Piezoelectricity, piɪeɪzoʊilɛk଼trɪsɪti, is the electric charge that accumulates in certain solid materials in response to applied mechanical stress. The word piezoelectricity means electricity resulting from pressure. It is derived from the Greek piezo or piēzīn, which means to squeeze or press, and electric or electron, which means amber, an ancient source of electric charge. Piezoelectricity was discovered in 1880 by French physicists Jacques and Pierre Curie. The piezoelectric effect is understood as the linear electromechanical interaction between the mechanical and the electrical state in crystalline materials with no inversion symmetry. The piezoelectric effect is a reversible process in that materials exhibiting the direct piezoelectric effect also exhibit the reverse piezoelectric effect. For example, lead zirconate titanate crystals will generate measurable piezoelectricity when their static structure is deformed by about 0.1% of the original dimension. Conversely, those same crystals will change about 0.1% of their static dimension when an external electric field is applied to the material. The inverse piezoelectric effect is used in production of ultrasonic sound waves. Piezoelectricity is found in useful applications such as the production and detection of sound, generation of high voltages, electronic frequency generation, microbalancers, to drive an ultrasonic nozzle, and ultrafine focusing of optical assemblies. It is also the basis of a number of scientific instrumental techniques with atomic resolution, the scanning probe microscopies such as STM, AFM, MTA, SNOM, etc., and everyday uses such as acting as the ignition source for cigarette lighters, push-start propane barbecues, and quartz watches. History, discovery and early research. The piroelectric effect, by which a material generates an electric potential in response to a temperature change, was studied by Carl Linnaeus and Franz Pinus in the mid-18th century. Drawing on this knowledge, both René Gestora and Antoine Céacute Sar Becquerel posited a relationship between mechanical stress and electric charge. However, experiments by both proved inconclusive. The first demonstration of the direct piezoelectric effect was in 1880 by the brothers Pierre Curie and Jacques Curie. They combined their knowledge of piroelectricity with their understanding of the underlying crystal structures that gave rise to piroelectricity to predict crystal behavior, and demonstrated the effect using crystals of tourmaline, quartz, topaz, cane sugar, and Rochelle salt. Quartz and Rochelle salt exhibited the most piezoelectricity. The Curies, however, did not predict the converse piezoelectric effect. The converse effect was mathematically deduced from fundamental thermodynamic principles by Gabriel Lippmann in 1881. The Curies immediately confirmed the existence of the converse effect, and went on to obtain quantitative proof of the complete reversibility of electroelastomechanical deformations in piezoelectric crystals. For the next few decades, piezoelectricity remained something of a laboratory curiosity. More work was done to explore and define the crystal structures that exhibited piezoelectricity. This culminated in 1910 with the publication of Woldemar Voigt's Buch der Kristallphysik, which described the 20 natural crystal classes capable of piezoelectricity, and rigorously defined the piezoelectric constants using tensor analysis. World War I and post-war. The first practical application for piezoelectric devices was sonar, first developed during World War I. In France in 1917, Paul Langevin and his co-workers developed an ultrasonic submarine detector. The detector consisted of a transducer, made of thin quartz crystals carefully glued between two steel plates, and a hydrophone to detect the returned echo. By emitting a high-frequency pulse from the transducer, and measuring the amount of time it takes to hear an echo from the sound waves bouncing off an object, one can calculate the distance to that object. The use of piezoelectricity in sonar, and the success of that project, created intense development interest in piezoelectric devices. Over the next few decades, new piezoelectric materials and new applications for those materials were explored and developed. Piezoelectric devices found homes in many fields. Ceramic phonograph cartridges simplified player design, were cheap and accurate, and made record players cheaper to maintain and easier to build. The development of the ultrasonic transducer allowed for easy measurement of viscosity and elasticity in fluids and solids, resulting in huge advances in materials research. Ultrasonic time domain reflectometers could find flaws inside cast metal and stone objects, improving structural safety. World War II and post-war. During World War II, independent research groups in the United States, Russia, and Japan discovered a new class of synthetic materials, called ferroelectrics, which exhibited piezoelectric constants many times higher than natural materials. This led to intense research to develop barium titanate and later lead zirconate titanate materials with specific properties for particular applications. One significant example of the use of piezoelectric crystals was developed by Bell Telephone Laboratories. Following World War I, Frederick R. Lack, working in radio telephony in the engineering department, developed the cut crystal, a crystal that operated through a wide range of temperatures. Lack's crystal didn't need the heavy accessories previous crystal used, facilitating its use on aircraft. This development allowed Allied air forces to engage in coordinated mass attacks through the use of aviation radio. Development of piezoelectric devices and materials in the United States was kept within the companies doing the development, mostly due to the wartime beginnings of the field, and in the interests of securing profitable patents. New materials were the first to be developed. Quartz crystals were the first commercially exploited piezoelectric material, but scientists searched for higher performance materials. Despite the advances in materials and the maturation of manufacturing processes, the United States market did not grow as quickly as Japan's did. Without many new applications, the growth of the United States' piezoelectric industry suffered. In contrast, Japanese manufacturers shared their information, quickly overcoming technical and manufacturing challenges and creating new markets. In Japan, a temperature-stable crystal cut was developed by Isaac Koga. Japanese efforts in materials research created piezoceramic materials competitive to the U.S. materials but free of expensive patent restrictions. Major Japanese piezoelectric developments included new designs of piezoceramic filters for radios and televisions, piezo buzzers and audio transducers that can connect directly to electronic circuits, and the piezoelectric igniter, which generates sparks for small engined ignition systems by compressing a ceramic disc. Ultrasonic transducers that transmit sound waves through air had existed for quite some time but first saw major commercial use in early television remote controls. These transducers now are mounted on several car models as an echolocation device, helping the driver determine the distance from the rear of the car to any objects that may be in its path. Mechanism. The nature of the piezoelectric effect is closely related to the occurrence of electric dipole moments in solids. The latter may either be induced for ions on crystal lattice sites with asymmetric charge surroundings or may directly be carried by molecular groups. The dipole density or polarization may easily be calculated for crystals by summing up the dipole moments per volume of the crystallographic unit cell. As every dipole is a vector, the dipole density P is a vector field. Dipoles near each other tend to be aligned in regions called vice domains. The domains are usually randomly oriented, but can be aligned using the process of poling, a process by which a strong electric field is applied across the material, usually at elevated temperatures. Not all piezoelectric materials can be poled. Of decisive importance for the piezoelectric effect is the change of polarization P when applying a mechanical stress. This might either be caused by a reconfiguration of the dipole-inducing surrounding or by reorientation of molecular dipole moments under the influence of the external stress. Piezoelectricity may then manifest in a variation of the polarization, strength, its direction or both, with the details depending on 1. The orientation of P within the crystal symmetry, and 3. The applied mechanical stress. The change in P appears as a variation of surface charge density upon the crystal faces, i.e., as a variation of the electric field extending between the faces caused by a change in dipole density in the bulk. For example, a 1 cc cube of quartz with 2 kilonewtons of correctly applied force can produce a voltage of 12,500 V. Piezoelectric materials also show the opposite effect, called converse piezoelectric effect, where the application of an electrical field creates mechanical deformation in the crystal. Mathematical description: linear piezoelectricity is the combined effect of the linear electrical behavior of the material, where D is the electric charge density displacement, epsilon is permittivity, E is electric field strength, and Hooke's law for linear elastic materials, where S is strain, S is compliance under short-circuit conditions, T is stress, and these may be combined into so-called coupled equations, of which the strain charge form is in matrix form, whereas the matrix for the direct piezoelectric effect and is the matrix for the converse piezoelectric effect. The superscript E indicates a zero, or constant, electric field. The superscript T indicates a zero, or constant, stress field, and the superscript T stands for transposition of a matrix. Notice that the third-order tensor maps vectors into symmetric matrices. There are no non-trivial rotation invariant tensors that have this property. That is why there are no isotropic piezoelectric materials. The strain charge for a material of the 4 mm crystal class as well as the 6 mm crystal class may also be written as, where the first equation represents the relationship for the converse piezoelectric effect and the latter for the direct piezoelectric effect. Although the above equations are the most used form in literature, some comments about the notation are necessary. Generally D and E are vectors, that is, Cartesian tensor of rank 1, and permittivity epsilon is Cartesian tensor of rank 2. Strain and stress are, in principle, also rank 2 tensors, but conventionally, because strain and stress are all symmetric tensors, the subscripts of strain and stress can be relabeled in the following fashion: 11.1, 22.2, 33.3, 23.4, 13.5, 12.6. That is why S and T appear to have the vector form of 6 components. Consequently, S appears to be a 6 by 6 matrix instead of rank 4 tensor. Such a relabeled notation is often called Voigt notation. Whether the shear strain components are tensor components or engineering strains is another question. In the equation above, they must be engineering strains for the 6 coefficient of the compliance matrix to be written as shown, i.e., engineering shear strains are double the value of the corresponding tensor shear, such as and so on. This also means that, whereas the shear modulus in total, there are 4 piezoelectric coefficients, and defined as follows, where the first set of 4 terms correspond to the direct piezoelectric effect and the second set of 4 terms correspond to the converse piezoelectric effect. A formalism has been worked out for those piezoelectric crystals, for which the polarization is of the crystal field-induced type. That allows for the calculation of piezoelectrical coefficients from electrostatic lattice constants or higher-order Madelung constants. Crystal classes. Of the 32 crystal classes, 21 are non-centrosymmetric, and of these, 20 exhibit direct piezoelectricity. 10 of these represent the polar crystal classes, which show a spontaneous polarization without mechanical stress due to a non-vanishing electric dipole moment associated with their unit cell, and which exhibit piroelectricity. If the dipole moment can be reversed by the application of an electric field, the material is said to be ferroelectric. Polar crystal classes 1, 2, mm2, 4, 4 mm, 3, 3 meters, 6, 6 mm. Piezoelectric crystal classes 1, 2, 222, mm2, 4, 4, 422, 4 millimeters, 42 meters, 3, 32, 3 meters, 6, 6, 622, 6 millimeters, 62 meters, 23, 43 meters. For polar crystals, for which P0 holds without applying a mechanical load, the piezoelectric effect manifests itself by changing the magnitude or the direction of P or both. For the non-polar, but piezoelectric crystals, on the other hand, a polarization P different from zero is only elicited by applying a mechanical load. For them, the stress can be imagined to transform the material from a non-polar crystal class to a polar one, having P0.